Hello. Today we'll begin the unit on chemistry fundamentals with a discussion on matter and measurement. So let's begin. The scientific method is probably something you've used before AP Chemistry without realizing it. It's one way to analyze the world around us. It represents a general approach to solving problems that involves making observations, seeking patterns in the observations, formulating hypotheses to explain observations, and testing these hypotheses by further experiments. Those hypotheses that withstand such tests and prove themselves useful in explaining and predicting behavior become known as theories. Overall, the process of scientific method is truly what makes science. As you know, there are three states of matter that have been taught in general science, which include solid, liquid, and gas. Each form displays simple, observable properties. A gas has no fixed volume or shape and demonstrates unique compressibility. A liquid has a distinct volume but does not possess a specific shape and therefore assumes the shape of the container it is placed into. A solid has both a specific volume and shape. As a fundamental basis of understanding chemistry, you need to understand that you are studying matter. And so this study of matter, such as solid, liquid, and gas, is important, and we'll be studying those changes that pertain to those states of matter. Looking further, the word matter refers to anything that has mass and takes up space. Essentially, you matter as you are made of matter. And as we go forward, we will explore how various types of matter are further classified. To begin, we look at atoms, which are considered the building blocks of matter. As building blocks, atoms can be combined to form elements or even compounds. A compound is made up of two or more different kinds of elements. For example, consider the fact that when hydrogen gas burns an oxygen gas, the elements hydrogen and oxygen combine. This forms water. Conversely, water itself can be decomposed into elements, compounds, via some type of electrical means such as hydrolysis. The observation that these elements are consistently the same in a pure compound is best described by the law of constant composition, or more commonly as Proust's law. Referencing back to the states of matter and their observable characteristics, one can see that as processed, the transition between states can be induced by cooling, compressing, heating, or through the alleviation of pressure. Matter can be further divided into two primary classifications, which include heterogeneous and homogeneous mixtures. In the case with heterogeneous mixtures, the components that contribute to a mixture are not uniform and, generally speaking, can definitely be seen as separate components that are placed together. Examples of which include Raisin Bran cereal, mud, or even chocolate chip cookies. Conversely, homogeneous mixtures are more uniform and can be further broken down into solution-based mixtures, such as a mixed concoction of apple and orange juice, or even pure substances. Now, the pure substances either operate as independent single elements like aluminum or even gold, or as uniform compounds such as the aforementioned water in the previous slide. The distribution of these categories can be further evidenced in the image seen where, on the atomic level, individual elements can be seen. In letter A, they can be seen as a molecule, or the same case would be more like a molecule of elements. In letter C, they work as a compound, or even in letter D, they can be conceived as a mixture. So now that matter has been classified, let us now take a look at both the properties and changes that matter undergo. We'll begin with looking at the concept of physical and chemical properties. Physical properties refer to observed characteristics in an unchanged compound or element. This means that the elemental arrangement of atoms used are not changed. Conversely, chemical properties are only observed during a change from one element or compound state to another element or compound. Going further, intensive properties are independent of the amount of matter present and include properties such as density, boiling, color, things of that nature, whereas extensive properties are more dependent upon the amount of matter present, such as mass, volume, or even energy. As a note of reference, physical changes represent changes to a compound that does not alter the composition of the substance. Conversely, during a chemical change, atoms are rearranged and used to form new substances. As chemical reactions fall under the envelope of being chemical in nature, this forms of change will likely be discussed more throughout the chemistry. So, there we go. Looking at the example presented, you see an example of compounds that can be broken down. As I mentioned prior, water can actually be broken down into smaller components of hydrogen and oxygen through a process called hydrolysis. All right, what you should see before you is a list of the chemicals that were produced in industry during 2002, and what should stand out is just the proportion of production that relates to the acids, bases, and pure elements respectively. Notice that sulfuric acid, represented by the chemical formula H2SO4, predominates and has the most production in pounds, and it's used primarily for fertilizer, chemical manufacturing. In fact, you can find sulfuric acid in your basic industrial Drano, where you use to unclog basically drains. Likewise, nitrogen and oxygen come in second, and those are pure elements, and those are heavily used both in chemistry for reactions, but also as fertilizers and or in steel welding. Phosphoric acid, although found in fertilizer, it can also be found in some sodas as a preservative. And then finally, if you notice, the base sodium hydroxide is perhaps the most notable base out there, and perhaps the strongest, but it's used in aluminum production as well as soap production. And so now we're going to switch gears here and discuss the separation of mixtures, and we're going to talk about the various processes that are involved in separating mixtures. And if you recall, there were two types of mixtures. There's homogeneous and there's heterogeneous mixtures. And depending on the means, you can separate a homogeneous mixture or perhaps even a heterogeneous mixture. So let's go ahead and get started talking about those techniques. The first step here is filtration, and during the use of filtration, it operates under the principle of being able to separate heterogeneous mixtures. In this case, you generally have an arrangement where you might have a funnel that's lined with some type of filter paper, and when you have your heterogeneous mixture, let's say that it's differentiated between a liquid and solid substance, you can actually pour the solution through the filter paper where the solid itself adheres to the filter paper, whereas the liquid is allowed to penetrate the filter paper and enter another container or receptacle to contain them. And this technique is very useful as a mixture separation technique for heterogeneous mixtures primarily. It would be synonymous with coffee filtration if you've ever seen that process. Now the next process, distillation, deals primarily with homogeneous mixtures. Those are mixtures that are less easily discernible in terms of the naked eye. These principles can be used to separate two miscible liquids such as water and acetone, or perhaps even water and alcohol. And they operate under the principle of the boiling point of the solution in question. Now, as far as the figure itself, on one end you have your actual solution that is heated using some type of heating apparatus, and it has a closed system. And as the vapor evaporates, it goes into a cooling system that is provided through cooling water, and during this cooling process, it causes that vapor to condense and form liquid droplets that can later be collected into a receiving flask. And this would operate under the guise of having two solutions that might have different boiling points. So let's say you have a solution that boils at 78 and one that boils at 100. If you want to separate those two liquids, you might set your temperature to somewhere at 80 degrees and have it heating until it reaches that temperature, and then collect your necessary solution material. And you can actually repeat this process over several times to refine the collection of what you acquire in your receiving flask. Now, another technique is very useful as well for homogeneous mixtures, and that deals with chromatography. In this particular method, it is used to separate material based on differences in solubility in various solvents. And you can actually manipulate the variation in the solvents used to adjust the degree of separation. Now, in the image provided, you just have a typical representation of what happens when you put a black marker on filter paper and then you add that paper to water. Now, the water acts as what's called the mobile phase. The mobile phase is what guides the movement of the material being separated. And so in this particular instance, because water is a notable polar substance, it causes the polar substances to move a little bit faster, whereas the more non-polar substances tend to stick or adhere closer to the bottom of the paper. And so again, it highlights the differences in solubility as well as polarity. And so this technique is very critical in separation processes, but it also can be applied to other forms of instrumentation as an extension of the chromatography technique. You can definitely employ this application. So overall, separation techniques are very critical and they're very useful for theories of chemistry. And a lot of times we know that we have a homogeneous mixture because they're not easily separated. We can't easily separate them, but using techniques such as chromatography or perhaps the filtration system, so forth, we're able to conveniently separate the two. So let's go ahead and switch gears here, and let's talk about units of measurement. Now, if you've already been experienced in chemistry, you have some kind of prior knowledge when it comes down to units of measurement. And so this should be kind of a miniature review. But to recap, there is a system of units that are applied universally among all sciences, and that's an accepted staple of how they measure things across all paradigms of science. And what that means is if you're measuring something and you use these units vernacularly, it makes the exchange of information a lot more easier to understand. So with that in mind, the SI units, or International Units of Measurement, for mass would be the kilogram, represented by the abbreviation kg. For length, it is the meter. For time, it is the second. For temperature, it is Kelvin. For the amount of substance, it is regarded as the mole. For electric current, it is the ampere. And luminous intensity is the candela. Now, of note is that in some instances, the SI units are comparable with the metric conversion. However, this is not always the case. In fact, in many instances where when you're talking about metric, the metric unit of choice for temperature is something in the order of degrees Celsius. For mass, it's represented as the gram. And so you want to be kind of mindful of these distinctions, as SI units are very pertinent. However, sometimes they can be overlooked when introduced to the metric system of units. So moving on in the discussion of units, we're going to talk about the metric system. And generally when I introduce the metric system, we use the popular mnemonic King Henry died drinking chocolate milk. However, the picture becomes a little bit more complex, and so you want to make sure that you become completely familiar with these other extensions of that metric system prefix, as these other units are just as important, and you're susceptible to seeing questions of the nature that deal with other various prefixes such as giga, perhaps pico, femto, and even nano to know. So you want to make sure you get a foundation of understanding those conversions. Now, another standing piece of information deals with the idea of volume. Now, volume in general, we commonly use in liter. However, it's generally thought to be in meters cubed for the standard measurement. And so being able to convert between those is a very strong precedent, very good piece of information. You want to be mindful that 1 cubic centimeter is equivalent to 1 milliliter as a staple of conversion. And so extending further into temperatures, I mentioned earlier how Celsius is the metric measurement for temperature, and the correlation between Celsius and Kelvin.
Excuse the interruption. If anybody's still missing any ESDT scores, please email Jennifer Jordan. Thank you.
All right. Looking back at the slide of temperature, you notice that there is 3 distinctions of Kelvin, Celsius, and Fahrenheit. With Kelvin, that is the more commonly accepted manner in which we calculate temperature. It is the SI unit of measurement. Celsius is also popularly accepted as it is used in the metric system. However, one must understand the conversion between the degrees Celsius and Kelvin as being a difference of 273. Fahrenheit is also pertinent, however, it's not highly discussed. And what should be gleaned from this particular slide is that the Fahrenheit, Celsius, and Kelvin all represent temperature, but temperature is basically a proportional measurement of the kinetic energy of the particles that are moving. And so, to recap, I mentioned that the scientific measurements are Celsius and Kelvin, with Celsius being the highly metric regarded one, and Kelvin being the one that is used primarily for the SI unit of measurement. And so Celsius was actually in doctrine based on many properties of water, where 0 represents the freezing point of water and 100 degrees represents the boiling point of water. Now for Kelvin, as I mentioned, it's the SI unit. It is based on the properties of gases, and 0 Kelvin essentially means 0 kinetic energy. And there is no such thing as a Kelvin temperature. In fact, 0 Kelvin is absolute 0, and it represents the coldest temperature possible. And again, highlighting what I mentioned before about the relationship between Kelvin and degrees Celsius, Kelvin is equal to degrees Celsius plus 273.15, which can be approximated to 273. For Fahrenheit, it's a little bit more complex, but the scale is not used in scientific measurements. The conversions for those two are provided, where you would just simply put it in the equation for if you're trying to solve for degrees Fahrenheit or perhaps even degrees Celsius. Now, density is one of those derived SI units. It is a physical property of a substance, and it represents a ratio of the mass of a substance to its unit of volume. And this generally can be represented as either grams per milliliter or perhaps even grams per cubic centimeter. And for all intended purposes, here are some examples of densities. Now, one interesting tidbit of information is that when given the density of various liquids, if you try to apply placing a solid object into a density of a liquid, the density can impact whether that particular substance exhibits buoyancy or the ability to float, or if it sinks down to the bottom. For instance, if you look at the density of water, it falls at 1.0, and certain solid objects such as balsa wood, which is a solid object with a density of 0.16, would actually float in water. Whereas the more solid objects that have a greater density, such as your table salt or your iron perhaps, or even gold, which has a density of 19.32, those will tend to actually sink down into the actual water. And so, kind of going a little bit further, we're going to talk about the uncertainty in measurement and how key that is in measuring the graduations and lines and looking at the meniscus of various objects. So let's go ahead and get started. So when you talk about the uncertainty, you have different measuring devices, and they incorporate a variation in terms of accuracy as well as precision. For instance, if you're looking at a graduated cylinder, they have various graduation lines, and you can kind of measure those using those lines. You have a syringe that's very useful. It has the same feature, followed by a burette. It's going to offer the same capacity, although what's different and unique about it is that it features a stopcock that allows you to dictate how much water is released. You have a pipette, which is used to kind of acquire a broad amount of liquid. And then finally, you have a volumetric flask, which typically has one definitive set volume, and it has a line to specify that one set of volume. And so when you talk about their specific nature and what type of volumes go where, your pipette is going to retain smaller volumes, whereas your volumetric flask can be applied to larger volumes of substance. And the former three of the graduated cylinder and syringe and burette can be used to determine those amounts of solvents or the amounts of liquid that you're using in terms of relative amount. So it really depends on the amount that you have. Now, getting further into exact versus inexact numbers, the exact appropriation is about 1,000 grams per kilogram. That would be more exact, and it gives you a more definitive unit of measure than something that's going to be more broader. And now, leading into significant figures, the term significant figures refers to digits that were measured. When rounding calculated numbers, we pay attention to significant figures so we do not overstate the precision of our answers. It also is useful in the application of these two calculations, and it helps with maintaining uniformity between scientists when measuring things. And so when we talk about significant figures, there's actually 4 rules that pertain to them, and those 4 rules primarily deal with the position and behavior of zeros. And so when it comes down to these rules, there are 4 separate rules, and those rules deal with first rule being that all non-zero digits are significant. That means any number that's 1 through 9 or features of 1 through 9 are going to be significant. Zeros found between 2 significant figures are actually significant, so all the zeros in rule 2 are going to be significant. The zeros found to the left are insignificant, meaning they do not count. And notice that the ones that are significant are highlighted in red. And then lastly, zeros at the end of the number are significant only if it is a decimal point. So the zeros on the right-hand side are only significant when there is a decimal point. And so highlighted examples are provided in that image. And so taking that a little bit further, we look at the extension of applying significant figures to the rules of rounding. Now, there's a distinction between the rules. For instance, there's a rule for multiplication and division, and there's a rule for addition and subtraction. All right, so when adding or subtracting is performed, the answers are rounded to the least significant decimal place. So it's more of a placeholder, and it works independently of the number of significant figures. It's more of where the placeholder is located. Conversely, with multiplication and division, the answer can be no more accurate than the least accurate number being used to select the answer. In this case, when it's performed, it's rounded to the digit that corresponds to the least number of significant figures in any of the numbers used during that calculation. Now, many times there's a distinction made between accuracy and precision. There should be a rote understanding that accuracy represents how close a measurement is to the true value, how right you are. And then precision deals with how consistent that data is. And so there's definitely a difference between the two, and you want to understand that dynamic, especially when it pertains to interpreting data, because they can tell two separate stories. And so going further, talking about dimensional analysis, all chemistry problems deal with dimensional analysis, and they're a necessary part of the calculation process. So here, when you're talking about that, you want to be able to convert using dimensional analysis, and part of that employs the use of something called the factor label method, where you focus on trying to cancel out the units by solving. And so there's a couple of questions when you're answering that question that you should be able to use to diagnose how to answer it. One is, what do I need on top? What do I need on bottom? What do I know? How do I get there? You'll always be given the conversion factors when you need them. So a lot of times you don't have to memorize them. You just need to understand the process itself. For instance, in this particular example, the speed of light is 2.998 times 10 to the 10th power centimeters per second. What is this in kilometers per hour? You know the conversions provided are 1 kilometer is equal to 1,000 meters, and so forth, so on. And you know what's on your top, what's on your bottom, and kind of from there you kind of work your way through solving problems of that nature. And so there's another example where you're trying to convert between cubic meters to liters, and the same process can be said where you're converting cubic meters to liters. And another example, you have, these are just examples. And that completes today's presentation. And that completes today's presentation on matter and measurement.